Okay, so looking at this and looking at everybody's, it does look okay. I did like how everybody did this. We have a copper aluminum half cell. We need some type of salt bridge. We have the copper over here, the aluminum over here. We would have aluminum cations in there and copper 2+ cations in there. So, and then we have a wire with a voltmeter up here. Okay, there's your diagram. I know at least one of you did it with the cell notation, which isn't quite what I asked, but you did get it right. Looking at everything, this is our strongest oxidizing agent, and this is our strongest reducing agent. Okay, so that's off your table there. I like how I saw everybody write down. We have reactions. Okay, so because we're gaining electrons here, this is your cathode half reaction, and this is your anode half reaction. So here's our cathode, and this one over here is our anode. Now, again, I want to stress the cathode is the solid. Okay, this is our cathode half cell, but the electrode is the cathode, the solid piece. Electrons go towards, because we need to gain them, they have to come from somewhere, they go towards the cathode. The anions are going to flow through the salt bridge, whatever's in there, nitrate ions or whatever that's there, but we did put down. And the cations will flow in the other direction. Okay. Now, I think for what I saw, you did it this way. You said that the half cell potential for this one was positive 0.34, and the reduction potential, no, it's not delta M. The reduction potential for this cell, well, it's not a reduction half reaction that we're writing. The reduction potential is negative 1.66, but since I flipped it, it's positive 1.66. This is where I get the cell potential is equal to the half cell reduction potential of the cathode minus the reduction potential of the anode. So we're going to get the same answer if I do it with my equation or you do it here. It is going to be positive 0.34 minus a negative 1.66, 2.00 volts.
It's just the cell potential is negative. That's just the cell potential. It doesn't matter.
Okay, we'll talk about this. If the cell potential is negative, think about what happens. If the cell potential is negative, that would mean your cathode reaction would be here and your anode reaction would be up here. What do we know about that type of reaction from before? Non-spontaneous. So it's not a voltaic cell, it's the opposite of a voltaic cell. So when you get a negative cell potential, that's our electrolytic cells that we're going to talk about today. Thanks, good question. Oh, and because we have a 9-volt battery, we have 2 volts, we connect them in series, we need 5 batteries, not 4.5, because we can't have half of the cell. That's essentially why it's 5. Even if it was 4.2 cells, we would still bump it up to 5. Okay, so by definition, and that question leads directly into it, A voltaic cell converts chemical energy into electrical energy. It's spontaneous. We trick the electrons to go through a wire, but it is a spontaneous reaction. Okay. The other ones that we do are electrolytic cells, where we force them. So in some cases, a voltaic cell can go like this, and then we can force the products back this way by using electrical energy. So if this, this is an exothermic process here, the reverse reaction is endothermic. Now, not all electrolytic cells are like batteries, right? Quite a bit of the time we're electroplating things. There's no battery involved. There's no forward reaction for it. But as I said earlier, electrolytic cell that we use all the time is our phones and anything that recharges. It is one that does reverse. Not all of them do. Okay, another example is the decomposition of water. So breaking water apart into its component elements. It doesn't matter how high you heat water, okay, even if you put it under pressure. It's not going to decompose into hydrogen or oxygen just because of heat. You actually have to add electrical energy to do that. There it is. So in this case here, I have to add 285 kilojoules of electrical energy to get it to break apart into hydrogen and oxygen. Okay. Now, you know that the molar enthalpy of formation of water is 285 kilojoules. The molar entropy of simple decomposition is this. Right? I have to force the electrons that are hanging around the oxygen. I have to force them, the electrical energy has to force them back to around the hydrogen and replace the oxygen here, because there's electrons that we have to share here. Okay? Now we do this with a battery or some type of electron pump. So I can hook it up to a DC converter, I can hook it up to a battery, etc. But you must add energy for this system, for an electrolytic system to work. Okay? Like any endothermic reaction, if you remove the energy, the reaction stops happening. This is an old, this NiCad battery, nickel cadmium battery, the equations that we had, these things were literally the size, the battery was literally the size of that tape dispenser. Or it could be. They could be about half that size, or they could be that size. That was your portable phone. There's a reason why a lot of people still wear belt clips if they were older when they had portable phones, because they just got used to having it out here, because you couldn't put it in your pocket. It was just huge. Okay? But we've got new battery technology since the 90s, thankfully. That's why we have phones. Because would you care to carry around something like this, 2/5 size?
No, choice.
Yeah, but if you did what my phone does.
Okay. So here is the voltaic cell of that nickel cadmium battery. It has cadmium, and then you have your, I don't even know what that one's called. This guy here in a solution. We get energy from this to give us this, right? Okay, so this reaction is spontaneous. I don't know what the charge is because this isn't one that's on our booklet. You can find this one in my big booklet, but I don't. So there's your net cell reaction. The electrolytic part, when you plug it into, it just reverses. Okay, so the cadmium hydroxide becomes your cathode, and the nickel hydroxide becomes your anode. And your energy must be added on this side. Now, as I said, there were a lot of problems with nickel cadmium batteries if you didn't drain it. If you didn't drain the battery, it wouldn't fully charge again. It had a memory. So if you recharged it when it was at 25% and you did that a lot, you would only get 75% of the battery life after a while. Like our battery, and a lot quicker than the lithium ion batteries do, because our batteries do eventually die. But this was a lot worse, so you had to drain it completely before you got to plug it in. So you always carry 2 or 3 of those big batteries with you in your car. Okay. The differences between voltaic and electrolytic cells. There's one, and that is it. The spontaneity and the standard cell potential. So voltaic cells are spontaneous and have a positive standard cell potential, where electrolytic cells are non-spontaneous and have a negative cell potential. Everything else is the same throughout. Okay, they're not changing here. We are forcing electrons to go from the anode to the cathode, but electrons do go from the anode to the cathode in both. The anions move towards the anode in both, and so forth. So everything is the same throughout, other than the spontaneity of the reaction. So everything we've learned with voltaic cells and other electrolytic cells, other electrochemical processes apply here. Okay? The cell notation is a little bit different in a lot of cases, because we don't usually have two half cells in something like this. Okay, so here we have the redox reaction when electricity is run through a solution of potassium iodide. Okay, so all we have is K plus, I negative, and water. Okay, so we're going to be, because there's no form of electrodes given there, we say we're going to have 2 carbon electrodes. Again, we don't have to worry about that, because we know that these guys are not going to give up electricity. Not give up electrons. Now, going through this, again, right off your data booklet, this is an oxidizing agent. This is a reducing agent. This is an oxidizing agent. And a reducing agent. Thank you for that. Which one of those is the strongest oxidizing agent? Okay. Water is your strongest oxidizing agent, and the iodide ion is your strongest reducing agent. Because the potassium is, I think, 2 from the bottom, if I remember correctly, and water is about 8 or 10 from the bottom. Okay. So what is that reaction? It's water plus and what does it give me?
H2 plus 2OH.
And it has a reduction potential of negative what? 0.83. And then the iodine is going to be 2 iodide ions. It's going to give me iodine solid plus 2 electrons. And its reduction potential Positive 0.54. Now, we flipped that one, so I best remember to flip the sign. So we have negative negative 1.37 volts. We'll talk about that in a minute. And then we have our net cell potential. So which one of those is going to be acting at the cathode? The one that is undergoing reduction, the other one that's gaining electrons. So this would be our cathode. This would be our anode. That's our net potential. And what do you think that negative 1.37 volts means?
That's energy.
Okay, so what does that mean? It's not so much the energy, but that per charge, yes, I need to apply 1.37 joules of energy for every coulomb of charge. So basically what this is here is your minimum cell, or the minimum voltage that must be applied to get this cell to work. So if I only apply a 1 volt to that, it's not going to work. It should work, and if I apply a 1.5 volt battery in this series, in this.
Shouldn't you just add them together?
Yes, once I flip this, once I change the sign,
Oh, you can just add.
then because you flip this direction, so now we need to flip the sign and I just add them together.
Yeah.
Okay. As I said, you can also do negative 0.83 volts minus positive 0.54 volts to get the same answer. This is just your cell potential of your cathode minus your anode.
I wasn't sure you were supposed to do this.
No, when you flip that, you just add them. You put it there. Yes? Yes, that means this is a non-spontaneous reaction. It will not happen. If you just let it sit there, it's not going to happen until you force the electrons from one place to the other place. So you have to connect a battery or some other type of electron pump. Okay? And at least 1.37 volts must be applied. Battery, a DC, a DC generator, something like that. Okay. Now, what are some of the things that we can see as this progresses? And where would you see it? What would the pH do?
Lower.
You're creating hydroxide, so it's becoming more basic. The pH would increase. At which electrode would you see the greatest change to start with? The cathode or the anode? We're creating the hydroxide ions at the cathode, so that's where you're going to see that pH change to start with. Okay? So you're definitely going to see that change at the cathode. What other thing are you going to see at the cathode?
Gas.
Bubble, right? Gas being created. Okay, and we should see a solid being created at the anode. And it's actually a brown solid. Iodine is brown. So, not that you have to know that. And so, You would see that at a brown solid at the anode, and up here you had the other stuff at the cathode. Okay. Any questions on that? Okay. So I talked about this here. We can get that this here that we did down here is the approximation, because this is not a cell at standard conditions, because we didn't have any H2 gas originally. We didn't have any hydroxide ions originally. No iodine original. So it's not a standard cell, but this 1.37 would be a good approximation of what we would get out of that. Now, I do want to talk about the cell notation for that in a minute. So what the cell notation would look like here, why is it over there? The cell notation would look like this. Okay? Because we don't have half cells here. We're just doing a solution of potassium iodide. So a electrolytic cell diagram might look like this. Carbon, carbon, and you might see that notation for a charge pump, or you might see that notation. And I'm actually not sure which way it goes. I should. Can't remember which one of these is positives and negatives. I think this might be positive, but I could be wrong. What's that?
Bigger one's positive.
So this is another way of writing a charge pump for that. So unlike voltaic cells, electrolytic cells tend to be placed in one barrel. Okay? So some of the things that we do is like breaking apart water, creating iodines for something like this. How many people are wearing silver or gold-plated jewelry? If it's plated, it was probably created with an electrolytic cell to plate it. I have no idea if your jewelry is plated or if it's real, but okay. So these are just the type of things that we're going to go through or would use for electrolytic cells. So there's our basic understanding of electrolytic cells. Yes? Choking, are you?
Just a little bit.
So again, and talking about that minimum, we must apply a minimum of that 1.37 if it was in standard conditions, but that's going to give us a good approximation what we would need to apply. Now, what do you think? What do you think is going to happen if I apply, instead of 1.37, I put a 9-volt battery across it? What's likely to happen? What's going to happen to the reaction? Probably going to happen quicker because the electrons have more energy crossing faster. Okay. Any questions on any of that? Some 8 questions for you.
Why do battery charges go in halves?
That would be, in my opinion, a battery charger. This is a guess, an educated guess, but still a guess. I would guess it's because the one that has the higher amperage would charge faster. So that's my guess.